Hey guys, today I'm going to be talking about the exponential function. So f of x equals e to the x, which I'm going to introduce today. We're going to begin by introducing the letter e, so that's Euler's number, and it has a quantitative representation in maths. So just want to start with a little introduction, which is, let's say that we're investing money in a bank account. It increases by 100% once a year. So that's pretty obvious that we've just doubled our money, right? Increase by 100% means you get what you've got, you add in that same amount, you've doubled your money, okay? Well, you might ask yourself the question, is it better, rather than just investing 100% once a year, to split it into 250% and do it twice a year instead? So what would happen if that's the case? I of x represents your investment multiplier. So what happens is we have our amount of money and we add a half to it. And then whatever that amount of money we have, we add another half to it, okay? So this is basically what you're doing to your money. This is an increase of 50% here. So let's just make this clear. This over here is an increase of 50%. Yep, and this over here is another increase of 50%, okay? Oh, 50%. Okay, so as you can see, you multiply these two things together, it's 3 on 2 times 3 on 2, which is 9 on 4, which is bigger than 2, yeah? Because our investment multiplier when we did 100% once a year was 2. You might ask yourself the question, what if we keep kind of doing this? So rather than doing an increase of 50% twice a year, let's do an increase of what is a 1/3 increase 3 times a year, so 33.3% recurring. So what happens there? Well, then you're just going to have 1 plus 1/3 times 1 plus 1/3 times 1 plus 1/3, which you can write as 1 plus 1/3 cubed, which is 64 on 27. Now, what have we realized so far? Well, 64 on 27 is bigger than 9 on 4, and 9 on 4 is bigger than 2, which was our initial investment multiplier. So it kind of looks like that the multiplication factor on your money increases as you split your interest into more frequent periods. So even though you can kind of look at it as overall, it's in some sense an increase of 100%, if you split it into more portions, so you split the 100% into more portions and more regular investments, then you're going to be actually making more in the long run. And the reason that happens is because it's basically what's called compound interest. So you're making interest off more money over time. So what you might ask yourself is, it looks like the more times you split it, the more money you're going to make. Does this pattern continue forever? Can we get to a point where if we split it infinitely many times, we can make an infinite amount of money? So surprisingly, the answer to this question is no. And I just want to show you a little pattern that happens over here. So if you do 4 splits, so this is 25% increases 4 times a year, you'd get a multiplication factor of your money of 2.44. You do 5 splits, you get 2.49. You do 20 splits, you get 2.65. 50 splits, you get 2.69. So like obviously 50 is significantly more than 20, but the difference in the multiplication factor roughly is starting to get quite close. So you can see what's happening. It's increasing as you split it more and more, but the rate of increase is slowing down because it looks like it's getting closer and closer to some number, okay? So this number that is getting closer and closer is called Euler's number, all right? It's represented with the letter E, and its formal definition is the limit as n approaches infinity of this thing over here, 1 plus 1 on n to the n. So as you can see, as n gets larger, that corresponds to more and more splits of the payment. And as n approaches infinity, what we end up getting is we get the Euler's number, okay? And that thing, if you put it into your calculator, you can see it's approximately 2.718, etc. Okay? And just to make one thing clear, this is not a recurring decimal and it's not a terminating decimal. So Euler's number is irrational, just like pi. Similar idea. Okay, so all we can think about right now is we've got this special number E, and it corresponds to 2.718, etc. And you're going to see very soon why E comes in handy. So I'm just going to start with graphs of e to the x. So we're all comfortable with exponential functions. We've seen them before. So 2 to the x and 3 to the x, which is this one. This one is 2 to the x, the yellow one, and then this one is 3 to the x. you know that it has this kind of shape, and they all have this common point 0, 1, because any number to the power of 0 is 1, except if the number is 0. Okay, so e to the x is the blue one, and it kind of lies between 3 to the x and 2 to the x, and that's kind of expected, right? Why is that expected? Because e is roughly 2.72, yeah? So it should be lying between 2 and 3. And this one thing I want to make clear is whenever you've got transformations of this form over here, so just to write it out, x prime is ax plus b, and y prime is cy plus d, then you end up with a function which looks like this, and this is just your transformed version of your exponential function. Now, lucky for us, and I kind of described this a little bit in the last class, we don't have to worry too much when we're graphing exponential functions about dilations, about horizontal translations, because when you go to graph it, a lot of that stuff is just captured in finding axis-intercepts. So let's have a look at a couple of examples. So question 1 wants you to sketch this graph over here, stating its range. So the key features, before I go in and sketch that graph, the key features of this thing over here is that it has a horizontal asymptote. All right, has a horizontal asymptote at y equals d. So that is completely dependent on its vertical translation. All right. The other thing that I kind of want to talk about is shape really quickly. Again, this is hopefully just a recap because you guys would have seen this before. So if we're talking about e to the x looks like that. So it has this intersection 0.01. And then this one over here is minus e to the x. So this one would have the intersection 0.0 negative 1. So I just want to make that clear. This is e to the x. This one is minus e to the x. It corresponds to a reflection about the x-axis. And then this one is y equals e to the minus x, which corresponds to a reflection about the y-axis. And then the last one is, looks like this, all right? And that one is y equals minus e to the minus x, and that corresponds to a reflection about the x and the y-axis, okay? So the idea is we want to find its shape, we want to find its asymptote, we kind of want to get an idea of what the drawing would look like, and then we want to find any possible intercepts, okay? So first question, let's sketch this graph. So the first thing is the asymptote is at y equals negative 2. Okay, the shape, because it's positive in the power and in the front, you just got this normal exponential shape. So what's going on if I kind of start to sketch it on the right-hand side? All right, what's going on? It has an asymptote at y equals negative 2, which might be down here. All right, and it has this shape. Okay, but we don't know whether it does this thing, or this thing. So we're going to go ahead and find those axis intercepts first. So for the y-intercept, you set x equal to 0. That's the easy one. You end up getting f of x equals 2 times 1 minus 2, which is 0. All right, the good news about that, just technicality here, but we want f of 0, not f of x. All right, so the good news here is if the y-intercept is 0, the x-intercept has to be 0, so it is already obvious what our graph's going to look like, and it is an exponential function that goes through the origin. All right, so what pieces of information do you have? You have the fact that you have an asymptote at y equals negative 2, and you have that it goes through the origin. All right, so hopefully that wasn't too tricky. Question 2 is using transformations. So we start with f of x equals e to the x, and we have these transformations, and we want to see what happens to it. So I'm just going to label them all. So this one over here is 1, and then reflection, in the y-axis is another one, and then a translation is another one, okay? So let's just label them 1, 2, and 3. So 1, what is that doing? Dilation of factor 2 from the x-axis, which means that your y prime is going to become 2y, all right? And then transformation number 2, we've got a reflection in the y-axis, which means that your x prime is going to become minus x. And then transformation number 3 is a translation of 3 units right and 1 unit down. So we are grabbing our coordinates that we've already transformed, which is 2y and minus x, and we are moving that 3 units right. So the x coordinate is going to get a plus 3 and 1 unit down. So the 2y is going to get a minus 1. So we end up with x prime equals minus x plus 3 and y prime equals 2y minus 1. All right, and then just the normal deal when you're trying to find the image of the rule, which is to make x and y your subject, plug them into the rule, and then rearrange. So what do we end up with? We end up with, we want to rearrange this. We get minus x equals x prime minus 3, which means that x equals minus x prime plus 3. Okay, so that's the first one. And then for the second one, we get 2y equals y prime plus 1, which means that y equals 1/2 of y prime plus 1. And now once we have x and y as the subjects, which is this one and this one, this is good news. We can just substitute it into the rule. So the rule is, first of all, we have to set y equals f of x. So our rule is y equals e to the x. And now you're going to replace y with the other thing that we found, so y prime, and x with x prime. What do we end up with? We end up with 1/2 y prime plus 1 equals e to the minus x prime plus 3, all in the power. Now we rearrange to make y the subject. So we get y prime plus 1 equals 2e to the minus x prime plus 3, which means that y prime equals 2e to the minus x prime plus 3 minus 1. Okay? And this is your final answer. But remember, you just want to not write it with primed notation anymore. You want to write it as a function. So your transformed function would be f of x equals 2e to the minus x plus 3 minus 1. All right, and this is your final answer. Hopefully that makes sense. So let's have a look at the last question as well. So we want to find a sequence of transformations which maps that function to the graph of your original function, which is like y equals e to the x. All right. So how do we approach this? The thing that you're transforming to gets the primed coordinates. The things that you're transforming from gets the non-primed coordinates. So we write it as y equals 2e to the 2 minus x over 3 minus 1, and that's being transformed to y prime equals e to the x prime. Now remember, even though this is the unconventional way when we go from the thing with the transformations to the thing that's just kind of like the standard form, it's actually the better way, because all you have to do is remove all the stuff from the outside of the exponential function for the original graph, so everything outside that circle, and you can do a direct comparison and get the transformations right off the bat. So what do I mean by that? Let's add 1 to both sides of the original function. So we get y plus 1 equals 2e to the 2 minus x over 3. And then let's divide by 2. So we get 1/2 of y plus 1 equals e to the 2 minus x over 3. And now what is the benefit of that? Well, all this stuff can be directly compared to all this. And then all this stuff can be directly compared to all this. And this is a really beautiful thing, because we end up with x prime equals 2 minus x on 3. And we end up with y prime equals 1/2 times y plus 1. Okay, so when you go to actually writing out your sequence of transformations, you just got to be a little bit careful about ordering here. So there's a couple of ways you can approach this. I would probably do it in a way, I'm going to be very careful here. So I'd probably just start with the x stuff first. So for the x stuff, well, if you write this as like, there's a couple of ways you can do this. I'll probably write it as minus bracket x minus 2 over 3, just because I think it's easier to see what's going on. So if you write it like this, what's happening first is it's the minus 2 because it's in brackets, and then it's the minus and the divided by 3, which is a dilation and a reflection. So the order we want to write it in is the translation first. So translation of 3 units right. And then the reflection. So this is a reflection about the y-axis. Yeah, because it's the x value being minus x, which means you flip about the y-axis. And then the dilation. So it's divided by 3, which is the same as times 1/3. So it's a dilation of factor 1/3. Oh, sorry. From the y-axis, because it's the x value being affected. All right, so that's the sequence of transformations for x. You've done all of them. Let's let that go now and have a look at y. So y, you've got the y plus 1 in brackets, the whole thing multiplied by 1/2. So BODMAS tells us that the plus 1 happens first. So what do? We get a translation of 1 unit in the positive direction of the y-axis or up, okay? Followed by the 1/2, which is a dilation of factor 1/2 from the x-axis. All right, and that is a sequence of transformations which maps your original function to y equals e to the x. Hopefully that makes sense. Just for the next task, we're going to be focusing on questions 1 to 6 in exercise 5b. Thanks for tuning in.